We're looking at one of the most ambitious, heartbreaking, and ultimately triumphant scientific expeditions of the 21st century, NASA's Genesis mission. It's a story that literally has it all. We're talking Hollywood stunt pilots in an orbit a million miles from Earth, a devastating high-speed crash, and a forensic puzzle involving 15,000 shattered pieces. Let's get right into this explainer.
So where do we come from? Really, everything starts with this single, profound question. Today, our solar system is packed with this dazzling diversity of planets, moons, and asteroids. But billions of years ago, it was just a uniform, swirling cloud. So how exactly did that homogeneous cloud turn into the wildly different environments we see today, like the ice geysers on outer moons, or the rocky surface right here on Earth? Well, to figure that out, we literally had to go find the original ingredients.
Stephen Brody, the program executive for NASA, really hit the nail on the head when he talked about the sheer audacity of this project. He said, "The Genesis mission, to capture a piece of the sun and return it to Earth, is truly in the NASA spirit, a bold, inspiring mission." And he wasn't exaggerating. They weren't just going to look at the sun through telescopes, because honestly, spectral analysis just isn't precise enough for modern planetary science. No, they were actually going to fly out into deep space, capture physical pieces of the star itself, and bring those pristine atoms back to labs here on Earth.
Which brings us to part 1, origins of our solar system, and the 5 billion-year-old fossil record.
Okay, so our entire cosmic neighborhood began as what we call the solar nebula. As this giant ball-shaped cloud of dust and gas started falling in on itself, mostly made of hydrogen and helium but peppered with elements from older, dead stars, it flattened out and began to rotate. The sun formed right at the center, and the leftover debris, that became the planets. Now, because the sun is just so incredibly massive, its outer layers actually still hold the original unaltered recipe of that ancient solar nebula.
And fortunately for us, nature gives us a way to access that exact recipe. See, the sun's outer atmosphere is slowly but constantly flowing off into space. We call this the solar wind. This steady stream of electrically charged atoms, or ions, acts almost like a perfectly preserved fossil record. So the thinking was, if we could just catch these particles before they're deflected by Earth's magnetic field, Genesis could grab a pristine snapshot of our solar system's starting materials.
Genesis was actually launched to solve a very specific, glaring mystery. Oxygen comes in 3 isotopes, O16, O17, and O18. But for reasons totally unknown to scientists at the time, the proportions of these isotopes vary wildly. We're talking completely different ratios on Earth, the Moon, Mars, and various asteroids. Finding the original baseline ratio of these isotopes directly from the sun, that would provide the exact missing puzzle piece to explain how our planets actually formed.
So how do you do it? Part 2, catching the solar wind and designing the Genesis trap.
Now, the solar wind isn't just one uniform thing. Genesis was packed with highly advanced electron and ion monitors to autonomously detect exactly what regime of solar wind was hitting the craft at any given moment. They were hunting 3 specific types: the slow bulk wind, the fast wind, and the violent coronal mass ejections. Depending on what kind of wind was hitting the craft, the onboard computers would deploy different collectors. Think of them almost like giant space tennis rackets. And these deployable arrays held coaster-sized hexagonal wafers made of incredibly pure materials. We are talking pure silicon, gold, sapphire, and artificially created diamond-like carbon. When the solar wind slammed into these materials at hundreds of kilometers a second, the particles literally embedded themselves many atom layers deep. These ultra-pure materials basically acted as a permanent celestial prison for the trapped solar matter, completely free of earthly contamination.
The outward journey itself was basically flawless. Launched in August 2001, Genesis cruised a million miles away from Earth to the Lagrange 1, or L1 point. This is this special, quiet spot in space where the gravities of the Earth and the Sun perfectly balance each other out. That allowed the spacecraft to maintain an incredibly stable halo orbit, well outside of Earth's interfering magnetic fields. By December, it started collecting.
And it stayed there for 850 days. For over 2 years, Genesis sat in the extreme quiet of deep space, continuously soaking up the solar wind. It was an unprecedented success. It gathered up to 20 micrograms of solar material. Now, that is about the equivalent of a few grains of salt, but those are arguably the most scientifically valuable grains of salt in human history. By April 2004, the spacecraft closed its canister, fired its thrusters, and began the long journey home. It was basically the calm before the storm.
Which brings us to part 3,
the hard landing, and the fall to Earth. September 8, 2004. At 9:55 a.m. Mountain Daylight Time, the sample return capsule slammed right into Earth's atmosphere over northern Oregon. It was traveling at an immense velocity, 11.04 kilometers per second. That's almost 25,000 miles per hour. Just to put that into perspective for you, the only human-made object to ever re-enter the atmosphere faster was the Apollo 10 command module.
As it hit the atmosphere, the capsule experienced a crushing deceleration force of 27 Gs. I mean, that is immense. But this extreme force was actually part of the plan. The capsule had built-in G-switch sensors that were supposed to detect this massive braking force, maintain electrical contact, and then trigger the sequence to release the parachutes right as the G-forces subsided. But the parachutes never deployed. Slowed only by its own aerodynamic resistance, the capsule went into a chaotic tumble. The scientific community could only watch in absolute horror as this priceless capsule hurtled out of the sky and smashed straight into the desert floor of the Utah Test and Training Range at 193 miles per hour. The sheer force of the impact broke the capsule wide open, completely breaching the inner science canister. What makes this so incredibly devastating is what was actually supposed to happen. NASA had hired elite helicopter crews, we're talking pilots who did stunt work for Hollywood, to fly over the Utah desert. The capsule was supposed to deploy a drogue parachute and then a massive parafoil at 20,000 feet. The helicopters were going to fly right in and snag the parachute with a massive space-age hook in midair. The whole point was to ensure those fragile wafers inside wouldn't experience even a slight bump from landing. So, what exactly went wrong? Well, the Mishap Investigation Board later revealed a heartbreakingly simple engineering error. Those tiny G-switch sensors we talked about, the ones responsible for detecting the atmospheric entry, their internal mechanisms were designed and installed upside down on the relay cards. Because they were inverted, it was physically impossible for them to ever make electrical contact during deceleration. The spacecraft's computer literally never knew it was falling. Part 4. Forensics in the desert and sifting through the wreckage. The crash site was an absolute nightmare. It was highly hazardous. Before they could even think about touching the science payload, recovery teams had to save the unexploded pyrotechnics that were supposed to fire those parachutes, not to mention venting toxic battery gases. And once they finally got it to a clean room, they were staring at 15,000 shattered fragments of delicate collector wafers. They had to navigate desert dirt, brine from recent rains, and ironically, the absolute most difficult contaminant to remove, the smashed spacecraft's very own structural lubricants.
But this is where the incredible foresight of the Genesis engineering team literally saved the entire mission. Knowing a rough landing was, at least a remote possibility, they actually designed the wafers for the different solar wind regimes to be slightly different thicknesses. By meticulously measuring the thickness of these shattered, millimeter-sized fragments in the cleanroom, researchers could blindly identify exactly which type of solar wind each tiny little piece contained.
Leading us to Part 5, Secrets of the Sun and Triumph from the Wreckage. Against absolutely all odds, the mission met its primary goals. The critical solar wind concentrator targets, they survived almost completely intact. Scientists practically invented new ultrasonic cleaning techniques on the fly to strip away the desert dirt without harming the embedded solar ions just beneath the surface. They successfully recovered that highly anticipated oxygen and nitrogen isotope data. They even unlocked massive new insights into the slow solar wind, which actually helps physicists understand the space weathering that changes the colors of asteroids we look at through telescopes. Amy Jurowitz, a scientist on the project, summed up the resilience of this team just beautifully. She said, "Whenever you get a sample back from space, you can always work with it." We actually had that part of our mission accomplished. You see, the public and the media, they just saw a catastrophic crash. But the scientists, they saw a treasure trove that had safely made it back to Earth. Despite the violent, dramatic end to its journey, the Genesis mission was a profound, indisputable scientific success. Genesis proved that humanity can literally reach out, grab a piece of our local star, and use it to decode a 5-billion-year-old history. But it leaves us with an incredible, lingering thought. If the dust of our sun holds the answers to how Earth was formed, what other secrets of our cosmic origins are out there just waiting for us to catch them in the dark? Think about that, and keep looking up.